Okay, so are you ready to dive in deep? Today we're going to try to wrap our heads around, well, everything.
Literally everything.
We're talking about atoms and molecules, those tiny building blocks that make up, well, us and all this.
Stuff around us.
That's right, the very fabric of reality.
And we're lucky enough to be diving into atoms and molecules. Sounds like a pretty dense read.
It's a foundational text, really gets into the nitty-gritty.
But that's what this deep dive's all about, right? Getting into the details, so let's get to it. Atoms and molecules, the fundamentals of chemistry. I have to admit, just hearing those words takes me back to high school chem class.
It's funny how those words can trigger memories, but honestly, understanding atoms and molecules is way cooler than any textbook can convey.
I hope so, because I'm ready for a crash course in cool. But before we break out the Bakers and Bunsen burners, I gotta ask, where did this whole quest to understand the building blocks of matter even begin? Was it always scientists in lab coats, or did it start somewhere else, somewhere a little more, I don't know, philosophical?
You're actually onto something there. It all started not in a lab, but with philosophers pondering the nature of the universe.
No way. Philosophers were into this stuff, like those toga-wearing thinkers from ancient Greece.
You got it. We're talking way back, around 500 BC. Think about a philosopher named Democritus in ancient Greece. He had this radical idea that if you kept cutting something in half, eventually you'd get to a point where you just couldn't cut it any smaller. He called these uncuttable particles atoms, which is actually where we get the word today.
Wow. So the ancient Greeks were basically onto something. They figured this out over 2,000 years ago.
It's pretty mind-blowing, right?
And get this, around the same time in India, a philosopher named Maharishi Kanad was having remarkably similar thoughts. He called these indivisible particles parmanu.
They were onto something, those ancient philosophers.
That's incredible. It's like they had this intuitive sense of the microscopic world without any of the fancy tools we have today. But how did we go from these early philosophical ideas to the concrete scientific theories we have now?
That's where the real journey begins. Over centuries, brilliant minds started piecing together the puzzle, conducting experiments, and refining those early ideas. And a key figure in this transition was Antoine Lavoisier, a French chemist in the 18th century.
Ah, Lavoisier. Didn't he have something to do with oxygen? Or was it the law of conservation of mass? See, this is what happens when you try to access those high school chem class memories.
You're definitely on the right track. Lavoisier is often called the father of modern chemistry, and for good reason. He really revolutionized the field, and that law of conservation of mass you mentioned, that was one of his big contributions.
Okay, so break it down for me, the law of conservation of mass in a nutshell.
In the simplest terms, it states that in a chemical reaction, the total mass of the substances involved stays the same. Basically, atoms are just rearranging themselves, not appearing or disappearing.
So it's kind of like a magic trick, but with atoms instead of rabbits. The atoms are just shuffling around, but the total amount of stuff stays the same.
Exactly. Imagine baking a cake. You start with your ingredients, mix them up, bake them, and you end up with a delicious cake. But the important part is that the total weight of the ingredients before and after baking remains the same. Nothing is created or destroyed, just rearranged. And that's true at the atomic level, too.
That's a tasty way to explain it. So this law essentially says that atoms are like tiny, indestructible Lego bricks, always there, just rearranging themselves into different structures.
You've got it. It was a game changer. And you know what? This realization actually paved the way for understanding another crucial principle, the law of constant proportions.
Okay, another law. This is already more laws than I remember from high school chem class. So what does the law of constant proportions tell us?
This law dives into the recipe of matter. It states that a specific compound always contains the same elements in the exact same proportions by mass. No matter what, the recipe stays consistent.
Interesting. So are you saying that every molecule of water, for example, always has the same ratio of hydrogen to oxygen?
Precisely. It doesn't matter if the water is from rain, a river, or even if you make it in a lab. The ratio of hydrogen to oxygen by mass will always be 1.8. 9 grams of water will always break down into 1 gram of hydrogen and 8 grams of oxygen. This happens because water is always formed by 2 hydrogen atoms bonding with 1 oxygen atom, the famous H2O.
Wow, that's incredible. So every drop of water everywhere follows the same tiny recipe.
Exactly. It all comes back to the atoms.
Which, speaking of atoms, brings us to the star of the show. John Dalton, the mastermind behind atomic theory. I've heard his name, of course, but never really grasped what he actually did.
Well, get ready to be amazed, because Dalton's work was truly groundbreaking. He took these fundamental laws like the ones we just discussed and wove them into a comprehensive atomic theory that underpins so much of what we understand about chemistry today. And what's even more impressive, this guy started his teaching career when he was just 12 years old. Can you imagine? 12 years old and already shaping young minds. Talk about a prodigy.
12 years old. I was just trying to figure out fractions at that age, let alone the fundamental laws of chemistry. But okay, let's talk about his atomic theory. It seems like it underpins, like you said, so much of what we know about chemistry.
It absolutely does. It's like the foundation upon which modern chemistry is built. And what's remarkable is that Dalton's theory, it's surprisingly elegant in its simplicity. He broke it down into these bite-sized pieces, postulates he called them, that each explain a specific aspect of how atoms behave, how they interact with one another.
Okay, I'm liking the sound of bite-sized pieces. Much easier to digest than some massive, complicated theory. So what's the first postulate all about? What's Dalton's starting point?
His first postulate states that all matter, everything around us, is made up of these incredibly tiny particles called atoms. And these atoms, they're the smallest unit of an element that can participate in a chemical reaction.
Okay, that makes sense. It echoes what those ancient philosophers were thinking, right? About those indivisible particles.
Exactly. Dalton provided the scientific framework for those early philosophical ideas.
He gave those ancient thoughts some serious scientific weight. Cool. So what about his other postulates? How do those build on this first idea of atoms being the fundamental unit?
Well, his second postulate, it directly addresses those laws we were discussing earlier. It states that atoms are indivisible. They can't be created or destroyed in a chemical reaction. They're just rearranged, like those Lego bricks we were talking about.
Ah, okay, so that explains the law of conservation of mass. If you can't create or destroy atoms, the total mass has to remain the same, even if those atoms are doing a little dance and rearranging themselves.
Exactly, you're getting it. And it doesn't stop there. Dalton's third and fourth postulates, they give us more specific details about these tiny particles. They state that all atoms of the same element are identical. They have the same mass, the same chemical properties, but here's the kicker. Atoms of different elements, they're different. Different masses and different chemical properties.
So all oxygen atoms are essentially the same, but they're totally different from, say, hydrogen atoms. That makes sense.
Precisely. And that difference, that uniqueness, is what gives rise to the incredible diversity of substances we see in the universe. And that leads us perfectly to his fifth and final postulate, which explains how these distinct atoms come together.
Okay, so is this where those recipes we were talking about come in? The ratios of elements in a compound?
You got it. Dalton's fifth postulate states that atoms, they combine in simple whole number ratios to form compounds. And this is the essence of the law of constant proportions, those fixed ratios we observe. They're a direct result of atoms always combining in whole numbers.
So you can't have like half an atom or fraction of an atom reacting with another atom. It's always 1, 2, 3, a whole number.
That's right. It's those whole number ratios that dictate the properties of a compound. Now, thinking about these incredibly small things, these atoms, it's kind of mind-blowing, right? How incredibly tiny they are.
I know, it's almost impossible to fathom. I once heard that a single human hair is about 80,000 atoms wide. It's like atoms are to a grain of sand what a grain of sand is to the entire Earth.
That's a pretty good way to put it. Our source material mentions that a sheet of paper, it's about 100,000 atoms thick. To measure something that's small, scientists use a unit called a nanometer, which is 1/billionth of a meter.
A billionth of a meter. That's like unimaginably small. It boggles the mind, honestly, that we even know they exist. But okay, atoms are tiny, they're the building blocks, but how do they actually come together to form, well, everything? The stuff we see and touch and interact with every day.
That, my friend, is where molecules come in.
Molecules. Okay, so this is like the next level up from atoms.
Exactly. A molecule is simply a group of two or more atoms that are chemically bonded together. Think of it like atoms holding hands forming a little atomic dance party.
I love that visual. Atoms cutting a rug on the dance floor. So just to clarify, a molecule is like a group of atoms hanging out, bound together, acting as one unit, right?
Precisely. Now here's where it gets even cooler. Molecules can be made up of the same type of atom, or they can be a mix and match of different atoms.
Okay, so like give me an example of each.
Sure. Take oxygen. The oxygen we breathe exists as O2, meaning two oxygen atoms are bonded together in a little molecule. That's a molecule of an element. Now think about water, which we already mentioned. H2O, that's two hydrogen atoms and one oxygen atom, all bonded together. That's a molecule of a compound.
So water is like the ultimate elemental mixer. But that little formula, H2O, I mean, it's everywhere, right? Water is essential for life. It carves canyons. It shapes landscapes. It's incredible to think that all of that, everything water is, comes down to those three little atoms bonded together.
It's mind-blowing, isn't it? And here's another layer of complexity. You can have molecules made up of the same element, but with different properties, just based on how many atoms are linked together.
Okay, I'm not sure I'm following. Can you give me an example?
Absolutely. Think about oxygen again. We have O2, which we breathe, but there's also ozone, O3, which is, well, let's just say it's not something you want to breathe in.
Okay, so same element, different number of atoms, different properties. So the arrangement and number of atoms, that matters as much as the types of atoms involved.
You got it. It's like rearranging the same letters to spell different words. Cat is very different from act, even though they're made up of the same letters, really.
That's a great way to think about it. So how do scientists keep track of all these different combinations? Is there some kind of, I don't know, a molecular cataloging system?
There is. Scientists use chemical formulas to represent the composition of molecules and compounds. It's like a shorthand, a way to quickly see the types and numbers of atoms present.
Okay, so it's like a secret code that unlocks the mysteries of a molecule.
Exactly. And just like any good code, chemical formulas have a specific set of rules. You start with the symbols of the elements involved, like H for hydrogen, O for oxygen, and so on. Then you use subscripts to indicate the number of each type of atom in the molecule.
So H2O means 2 hydrogen atoms and 1 oxygen atom, just like that.
You're a natural. You've cracked the code. And for compounds with those charged atoms we talked about earlier, ions, we use parentheses to group them together. For example, calcium hydroxide, which you might know as lime, is written as CaOH2.
Parentheses, subscripts, it's like learning a whole new language. But it's fascinating how much information those formulas contain. It's like a tiny little window into the world of molecules.
It's an elegant system, really. And it gets even more interesting when we consider something called valency.
Valency. Okay, you just listen to me a little. What's valency?
In simple terms, valency is like the combining power of an element. Think of it like this. Imagine an octopus, right?
An octopus. I'm picturing 8 tentacles. Incredible intelligence. But why an octopus?
Because each tentacle represents a valency bond, a connection an atom can make with another atom. Now, let's say each human has 2 hands, and each hand represents a bonding site. If our octopus friend wants to hold hands with multiple humans using all its tentacles, how many humans could it hold?
Let me see. 8 tentacles, 2 hands per human. It could hold hands with 4 humans.
Exactly. The octopus, with its 8 bonds, could hold hands with 4 humans, each with their 2 bonds. We could even write this as a formula, OH4. The subscript 4 tells us the octopus O is bonded to 4 humans, H.
I get it. So the octopus is like an atom with a valency of 8, and each human is like an atom with a valency of 2. That's a really clever way to visualize it.
It's a simplification, of course. There are different types of bonds, and things can get a bit more complex, but you've got the basic idea. Understanding valency helps us predict how atoms will combine and what kind of molecules they'll form.
It's amazing how much information is packed into these chemical formulas. It's like having a superpower, deciphering the secret language of molecules. But speaking of superpowers, let's talk about molecular mass for a moment. Earlier, we discussed atomic mass, which is the mass of a single atom. Is molecular mass just taking that a step further, like adding all the atoms in a molecule together?
You're on fire today. That's exactly what it is. Instead of looking at the mass of a single atom, we're looking at the combined mass of all the atoms in a molecule.
So it's like if you have a basketball team and you want to know the total weight of the team. You would just add up the weight of each player, right?
Perfect analogy. You just add up the atomic masses of all the atoms in the molecule to find its molecular mass. And we use atomic mass units, or U for short, to express these masses. For example, hydrogen has an atomic mass of about 1 U, and oxygen is about 16 U.
So for water, H2O, you would add up the mass of 2 hydrogen atoms and 1 oxygen atom. That would give you the molecular mass of water.
You've got it. The molecular mass of water would be about 18 U, 2 times 1 U for the hydrogen, plus 16 U for the oxygen. Easy peasy.
Okay, that makes sense. But what about compounds that are made up of those charged atoms, the ions, like sodium chloride, which is just table salt? Do they have molecular mass too?
Another great question. You're really full of them today. For ionic compounds like table salt, we use the term formula unit mass instead of molecular mass.
So instead of a molecule, we talk about formula units, which are like the simplest ratio of ions in an ionic compound.
Exactly. You've got a knack for this.
Yeah.
And we calculate the formula unit mass in the same way as molecular mass by adding up the atomic masses of all the atoms in the formula unit.
So it's essentially the same idea, just a slightly different term depending on what type of compound we're talking about. It's amazing. We've covered so much, from ancient philosophers to John Dalton's groundbreaking theory to chemical formulas, valency octopuses. My brain is a little bit fried.
It's a lot to take in. But don't worry, you're doing great. And the most fascinating part is that this is just the tip of the iceberg.
It really is just the beginning, isn't it? We've gone from these big existential questions about what the universe is made of to the incredibly intricate world of atoms and molecules. It's mind-boggling.
It really is. And the crazy thing is, even though we can't see them with our naked eyes, we've developed these incredible tools to study them. Electron microscopes, imaging techniques. It's like we found ways to make the invisible visible.
It's incredible to think how far we've come. But it makes me wonder, if we could actually see the world at the atomic level, what would it look like? Would we see these tiny particles, these atoms, constantly whizzing around, bouncing off each other?
Imagine seeing the air shimmer with countless molecules, or watching water transform from a placid liquid into this intricate, crystalline structure as it freezes. It would be like having microscopic vision, but on a whole new level.
Yeah. We'd be able to see the invisible forces that govern our world, the interactions between atoms that create everything we see and touch. But as amazing as that visual would be, I have to ask, what holds those atoms together in the first place? Why don't they just fly apart?
That is the million-dollar question, isn't it? And it leads us to the fascinating world of chemical bonds. They're like the glue that holds atoms together, dictating how they interact, how they form the molecules and compounds that make up our universe.
Chemical bonds. It seems like we've stumbled upon yet another layer of this incredible microscopic world.
We have. And sadly, we're out of time for today.
I know, right? Time flies when you're having fun with atoms and molecules. But that's the beauty of a deep dive. There's always something more to discover, always another layer to peel back.
Absolutely. And who knows what wonders await us on our next journey into the hidden realms of science.
I, for one, am excited to find out. But until then, keep those brains buzzing, and remember, curiosity is the fuel of discovery. Thanks for joining us on this deep dive into the building blocks of, well, everything.
It's been my pleasure. Until next time.